Welcome students. So the next lecture of this transistor series, common emitter transistor amplifier, DC load line and operating point, we shall cover here. So I was out of station for a few days, so could not make the videos. So now onwards, once again you will get these videos regularly. So let us have a look at the transistor which is working as an amplifier under the CE configuration. So this is the circuit diagram of the transistor, and if you see here that VBB, this VBB and VCC, these are the bias voltage. Now their magnitude should be such that they should always keep the emitter base junction, that is JE, in forward bias and JC in reverse bias. So that should be the magnitude of VBB and VCC. Now if a DC bias voltage is not provided, so if we are not providing this VBB and VCC, and directly if we apply this AC voltage here, then what will happen? During positive half cycle, this will conduct. During negative half cycle, this will not conduct. So it will act like a rectifier. So the purpose of the transistor will not be solved. So that is why we are providing this bias voltage, making sure that the JE is always in forward bias and JC is in the reverse bias condition. Otherwise, it will upset the objective of the transistor operation. Now, as the first step, if we do not apply any signal here, so under no signal condition, we'll have, due to the bias voltage VBB, we'll be having JE is in the forward bias, and as a result of that, a DC collector current will be flowing. So at the output section, whatever current will be getting under no signal applied condition, we'll call it zero signal collector current. So this is an important term, the zero signal collector current. So this is a DC current. Okay. Now as the second step, now we are applying some input signal. Now if we apply some input signal, then we'll have the forward bias on JE, and that will keep on increasing or decreasing depending on whether the signal is positive or in the negative half cycle. Now during the positive half cycle of the signal, the forward bias on emitter junction is increased. Now as a result of that, the total collector current IC will also increase, and the reverse will happen during the negative half cycle of the signal. Now if we have a look into this figure, then we find the total collector current, which is denoted as small I capital C. So this notification are very important. This notation, whatever we are using, I capital C. So this is the total collector current. Now it is having two parts. One is the DC current. This capital I capital C, we are denoting this. This is basically your zero signal collector current. And another part is the AC part. So that is small I small c. So we can write that small I capital C, which is the combination of capital I capital C and small I small c. So this is the AC collector current. So this is DC collector current, this is AC collector current. Together what we are getting is the total collector current. So these are the two major conditions when transistor is working as an amplifier in the CE configuration. Now the next topic is the load line. Now what is this load line and why do we require this load line? So let us first try to understand the necessity of the load line. Now whenever we are using the transistor in a circuit, For this analysis, we generally require to determine the collector current at different values of collector emitter voltage. So earlier also we have seen that the input section and output section in our previous lectures, that there we have seen at the output section we need to establish the relation between the collector current and the voltage between collector and emitter. So with respect to this collector emitter voltage, we need to find the values of collector current. Now it can be found easily from the output characteristics, but finding this from the output characteristics is not a convenient solution of this problem. So a better solution can be obtained from the load line analysis. So this is a better method or an appropriate method to find the collector current at different values of collector emitter voltage, and hence there is a necessity for the load line analysis. Now let us try to understand what is load line. There are two types of load line. One is DC load line and there is AC load line. AC load line we are not going to discuss here. That will be the part of advanced electronics. This is what we are studying, the basic electronics. Now if we see once again, this is our transistor working in the CE mode. So all DC signals here, we are not providing any AC signal, and trying to find the DC load line. AC load line we are not finding here. So here we have the input section and output section, and if we concentrate on the output section, then we find here, if we apply KVL in this particular loop, if we apply KVL, then what we find that VCC minus VCE, this is VCE minus the drop IC to RC, this particular drop. So that will be equal to 0. So that means VCE, that is equal to VCC minus IC into RC. This is a very important equation for the transistor amplifier analysis. Transistor amplifier working in the CE mode. So that is a very important relation. And here if we see, then the DC load line, it is actually the maximum value of the collector current and the maximum collector voltage applied, VCC applied. So VCE can have the maximum value as VCC. So if we join these 2 points, then we call this particular line as the DC load line. Now question is, how do we find this? So to find this, we can consider this equation 1, and let us find a point A. Okay, so point A, if we find for point A, let us consider VCE equal to 0. So when VCE equal to 0, then from equation 1, what we find that 0, that is equal to VCC minus ICRC. So that is giving us the value of IC as the VCC by RC. So that is the maximum value of IC, and a point we are getting, this point A, that coordinate in VI characteristic line or the output characteristic line, we can write it as 0 VCC by RC. So this is what we have obtained, point A. Similarly for point B, let us consider IC equal to 0. So when IC equal to 0, what we obtain from equation 1, VCE, that is equal to VCC minus 0. ICRC value is 0, 0 into RC. So that means VCE can have the maximum value as VCC, and maximum we can obtain when there is no drop across the RC. That is the maximum value of VCE can have. So under these circumstances, point B is having its coordinate as VCC 0 on the VI axis, VI characteristics or output characteristics. So here you have VCE and here we have IC. So the point A is here, which is having a coordinate 0 VCC by RC, and here we have another point, say point B, which is having a coordinate VCC 0. So if we connect these two, we are getting our DC load line. So this is how we find the DC load line. So DC load line is the function of maximum current IC and maximum voltage VC. So by joining these 2 points, we can find the DC load line. So we can say from here that the variation of the output current as the function of load resistance RC with respect to the variation in the output voltage. That is what we are saying the DC load line. Now on the DC load line, there is an important point which we call as the operating point. Now what is this operating point? It is the zero signal values of IC and VC. So when we are not applying any AC signal. So zero signal values of IC and VC are known as the operating point. So operating point naturally is a point on the DC load line. So this operating point, why it is called operating point? Because the variation of IC and VC take place about this point when any signal is applied. That means it is providing a reference to us on the basis of which the variation at the output will take place. And it is also called quotient point. Quotient means silent, or popularly known as Q point. Now because it is the point on the output characteristics, and when the transistor is silent, that is no signal applied. Now let us try to understand with the help of an example. So suppose the input signal is absent and the base current for which say IB equal to 5 microampere. This is arbitrarily we are taking. Now under these circumstances, if we draw the DC load line, suppose this is our DC load line. So this is our point A and point B. So these are the DC load line, and with IB 5 microampere when there is no signal applied, the variation in VCE, for VCE the variation of IC, suppose it is of this kind. Now this line, wherever it intersects the DC load line, that is what we call as the operating point, or very popularly known as the Q point, quotient point, or silent point. So under zero signal condition, we are obtaining this. Now this Q point, if we have this Q point at the middle, then only we will be having a faithful amplification. So if we, what is faithful amplification? That means input signal and output signal, that will be the exact replica but in amplified form. So here you see all the part of the input signal are amplified. Only thing is that there is something called phase. There we have the 180-degree phase difference at the output for CE mode. So this is one important point you should note, 180-degree phase shift between input and output of CE mode. So phase shifted version, 180-degree phase shifted and amplified version will be getting. So each point in the input signal is equally amplified. So we call this is a faithful amplification. Now suppose this operating point is here. So as a result of that, what we'll get? We'll get this thing more, and here we'll get this as less. So we'll not get a faithful amplification. So for faithful amplification, it is very important that the operating point should be at the middle, or it should be the midpoint of the DC load line. Okay, so this is about the C amplifier as under the condition of common emitter configuration, and here we have learnt about the quotient point and we have learnt about the DC load line. So next lecture we may take on some numericals also. Thank you.